All right, I assume you'll all let me know if something's gone wrong with my slides or presentation, but so I'm going to talk about astrometry and data management. I want to particularly call out two people who've helped a lot with this. John Pareko has actually been the point person doing a lot of the work on our astrometry fitter, and Claire Saunders helped quite a bit at the last minute putting together some plots to characterize how we're doing right now. So like so many other talks from the project in particular, I'll talk about what we do right now in sort of a descriptive sense, how we're doing, and then I want to split up the question of what we'd like to be doing into two different parts. One for sort of constraining the astrometric transforms, the coordinate systems, and the relationships between them, and then how we'll actually measure object parameters. Now I know that you can't actually do those separately, but you have to do them consistently. But there are subtleties to each part that I want to call out separately. So what we do right now is really focused on HSC. This is the data set that we've processed at scale with the pipelines as they exist. And so while the code we're running was absolutely intended for LSST, all the results here you'll see right now are for HSC. So we fit a composite transformation model. Gary described a much more sophisticated one. Ours is quite simple right now, which we simply compose a transform from CCD pixels to focal plane, and that's just a linear transform, and then a polynomial transform from focal plane to tangent plane. And that's intended to include both the optics and the atmosphere, which the way we're doing it are essentially totally degenerate. And then there's actually a tangent plane to sky projection as well, but that's fixed by a Bohr site. We fit this model simultaneously for the transformations and the true positions of the matched sources. Gary mentioned how he treated the source parameters as nuisance parameters and marginalized over them. That's one difference between how we fit our models right now. The data includes the matched source positions and reference catalog positions. And the fit is done via an iteration over sparse Cholesky decompositions. And we use a rank update approach to avoid a full factorization every time we reject an outlier. And then we fit this model to all visits in each band overlapping a tract at one time. And a tract is a region of sky roughly the size of a focal plane, but so we fit all of the visits that with dithering touch that patch of that tract on the sky at one time. So this has a couple downsides that are probably already obvious to some of you. The first one is that we're fitting the CCD to focal plane transformation for different patches of the sky. And that's not necessary. We expect them to mostly stay in the same place. And if they change, that should be a function of time, not a function of position on the sky. And this does seem to be actually picking up some of the astrometric offsets. I actually took a look last night to see whether the CCD positions remain constant. They don't. This doesn't, I think, affect our repeatability right now. It does affect it means that we're not fitting what we thought we were fitting with those models, but there's enough degrees of freedom to actually fit what we see at some level. So that's a bit of a problem. It would be nice to be able to separate these into two different components along the lines that Gary did. With the way we're doing the fit, they're degenerate, but the optical distortion is much higher order. And if you could separate that and fit a mostly static term, then of course the fit for the atmosphere only could use a much lower order function, and that would be simpler and have less degrees of freedom overall. You may have also noticed that I said that we fit the true positions of sources. We don't actually fit for proper motion or parallax in these models right now. And I think this is the single biggest problem in what we're doing for astrometry, and it's probably enough to make some of you uninterested right now in terms of what we're doing right now. And you'll be hopefully more interested later when I talk about what we hope to do instead. It's also worth noting that this sparse matrix approach was something that worked well for a long time for us because it works quite well for less than 50 visits. But we've recently started processing data that has a few hundred visits both, and it's really slowed to a crawl for both of these. Again, this is the HSC ultra deep fields, and we're running into the fact that we're using a third-party solver that's sort of a unique one, and that's not parallel. So if we wanted to make it parallel, we would have to invest time in doing that. Finally, we also fit all the visits in one band at a time. We do not fit across multiple bands at a time. And that means both that we can't use the fact that the same star is, at more or less the same position, or at least its motion is consistent across measurements in different bands. and we can't fit chromatic terms to our models yet. So despite all of that, I think the picture of how we're doing is not quite as bleak. Here's some plots of matched source repeatability. This is traditional per object repeatability, and as a function of magnitude. Here's a zoomed in version of those. And you can see that we're getting sort of 10 milliarc second, 15 milliarc second repeatability at the bright end. And this is good enough that if you are not trying to do astrometry science, this is not the tall polar internet processing anymore. You care much more about the problems we have with deblending or backgrounds or photometry, because this isn't adding considerably to the size of the PSF. There are going to maybe be some systematic limited science like weak lensing that might be affected by systematics in these fits, but I think this is good enough for most people, but I think we're under no illusions that it's good enough for people who care deeply about astrometry. If you zoom, I'm going to zoom in now on just the 19 to 23rd magnitude. And if we plot that now on the x-axis, this is the peculiar velocities in arc seconds per day that you get from sort of fitting each star and saying, how much could those proper motions that we're not fitting be contributing to the scatter. It turns out for the actual requirements for LSST, going all the way back to the big SRD document, our requirements on astrometry are actually on a different metric. This is defined on the repeatability of distances between pairs of bright isolated stars on different scales. And the reason for this was to try to average out stochastic effects like photon noise and atmospheric turbulence, and get at how rigid our system is. We of course are only applying these to HSC data right now. It has different pixel sizes, much better seeing, much longer exposures, many fewer epochs. So it's not really, I'm not at all confident that these numbers will translate directly for LSST, but they're the best way we can measure these things in the absence of actual LSST data. And according to these, we're actually hitting these metrics pretty well. The minimum design stretch goals are down here. We're certainly within the design goal and hitting the stretch goal for a good chunk of, this is just a piece of the HSC survey. As you saw in Eli's slides, that HSC is many different fields that are quite widely separated. This was sort of the largest, mostly contiguous one. And you can see how these metrics vary over that area. This is, each one of these little super pixels is one tract. So that's the region in which we do one of these fits. The numbers, of course, are much smaller than the repeatability, the per object repeatabilities I showed earlier. And that's because, again, they're designed to average out the stochastic terms, which, as Gary mentioned, are the dominant parts, or at least very important parts of getting astrometry right. Here's the same thing at 20 arc minutes. It looks almost exactly the same. So what would we like to be doing? And then in here, I want to focus on the transformations side of that. First off, we need to switch to Gaia as the reference catalog. We're actually still using the Pan-STARRS catalog as a reference. I'm not even sure that we're using the one that's been recalibrated to Gaia. This is just technical details and different things getting prioritized. We're very close to getting this done. It's a little bit complicated because it means that we have to switch over our photometric catalogs, or we need to separate the photometric catalogs. That work has been done. And it means Gaia has fewer stars in the magnitudes we care about. And so for applications like just blind fitting a CCD to bootstrap it, that gets a little bit harder with Gaia. We absolutely need to include the reference catalog, proper motion and parallax, and of course go a little bit further than that, include the proper motion and parallax parameters of the things that we fit internally, the stars that are not in the reference catalog. And then we need to start predicting DCR offsets from the broadband colors. We also need to start doing a more sophisticated model of the actual transformations themselves. We'd like to be fitting many more composed terms, true CCD pixels to ideal CCD pixels. This is the electric field effects of various kinds. This would be something that's more or less temporally constant. Ideal CCD pixels to focal plane. Again, that's very close to temporally constant. focal plane to tangent plane without atmosphere. This is something that is, not totally constant, but very slowly, or varies in ways that are associated with the physical degrees of freedom of the optics. And it may be a little bit wavelength dependent. And then of course there's the atmospheric distortions, which I think are nuisance parameters at this point. And this, we'd like to fit that, well, we'd like to hold these transformations fixed and then just fit the atmospheric distortions and the physical degrees of freedom to each visit or tract. Now, it's not a coincidence that that sounds a lot like what Gary described this morning. And I think we have always considered the work he's done with DECAM to be sort of a model for how we'd like to approach with LSST. We've long had a different code base that applies a different approach to the fitting, but we'd like to use essentially the same kinds of models. At this point, I think it's fair to say that his code has a substantial lead on ours in terms of functionality. And he handles the linear algebra a different way. Instead of using sparse matrices, he's essentially marginalizing over many of the parameters so we can use dense matrices. And that may scale better and address some of the scaling problems we've run into. So we've been evaluating switching to actually using his code. The integration is not super trivial. There are big complex code bases that would have to be tied together, and it's a hard software engineering problem. But it's very much on the table, and I think we're evaluating whether it's the best use of our developer time right now. So once we've measured those transformations, that's, I think, probably the hardest parts of measuring object motions in terms of avoiding systematics. But there are still some catches for measuring object motions in LSST that are not necessarily there for other surveys, and I think it's worth calling those out. So first, I have to talk about why, or what we had originally planned to do for LSST. And this gets back to my talk yesterday on coads, where I mentioned that we were no longer planning to do multi-epoch fitting. And the original plan for stellar astrometry measurements on objects was multi-epoch fitting. We would build, detect, deblend, and measure static sky objects on the coads, and that would include slowly moving things. But for each one of those, we would load its pixels from all the single visit images and fit a 6-parameter model. That'd be 2 position parameters, 2 proper motion parameters, a parallax, and a flux. One flux, we would assume that if there was variability, it would not affect the fit to the motion. This was similar to what Dustin Lang did on Stripe 82, but I think there was a few flaws to this idea from the beginning. The first one was that we never had a coherent story for how to handle blending. We're planning to run a deblender on the coad, but of course these are objects that by definition are in a different place and blend differently with their neighbors on single epoch images. And if you use the coad deblending, even if you could devise a way to somehow project your coad deblending outputs down to single epoch images, you would almost certainly be biasing your measured positions towards the coad positions, or the average positions. And you can imagine ways to solve that problem, but you can also imagine ways to not try to solve that problem. I think that's what we'd prefer to do. And finally, the same problem that multi-epoch fitting has, I think, across the board, is that it's an inefficient use of compute resources. It's the brute force approach, and it's good because it's straightforward, but it's bad because we're going to be compute resource constrained, and we need to find more clever ways to try to get the same information out of the data. So what we'll do instead, it involves a few different pieces, and I want to start with, I think, the most conservative, most obvious, most familiar one of those. And that is, if we're going to be doing joint fitting in catalog space of all of our per epoch positions, all of our source positions, in order to constrain the transformations between different images, then we will be getting those parameters out. And this is what everyone does for astrometry right now. It's the tried and true state of the art. And there's a lot of subtlety in doing it, but once we fit for those parameters, that gives us, for many objects, what we'd hope to produce. But for LSST, if you remember back to Yutra's talk yesterday, we're planning to detect objects on coads and from combinations of difference images. We're not planning to match all of the sources that we detect on direct single images and turn those into objects. The blending is totally different. The depths are totally different. The number of neighbors is totally different. It's a really, really hard, ambiguous matching problem. So essentially, we are measuring stellar motions the traditional, tried and true way on the wrong set of objects. And so You can imagine matching those to the objects and reporting the motions for those. And I think that's essentially our worst case scenario, that the objects that don't match well to those, or where there's ambiguous matches, we don't have stellar motion parameters for the ones that we can't match well. So I think that if we can get to that point, that's getting us to the state of the art, but we'd like to push to a little bit beyond that. Another piece of the puzzle is that we'll eventually be making yearly coads. Yearly doesn't necessarily make sense for DR1, but the idea of these was always to detect high proper motion stars that may smear out in a full survey coad, but would be quite visible, and their motion would be less than the PSF size or a quarter of the PSF size in a single yearly coad. If you can detect them in those yearly coads, you can also fit proper motions to the suite of yearly coads, and that's much less inefficient than fitting to the suite of all the input images. And for things that slowly move, or move quickly in the case relative to other stars, slowly relative to asteroids, then you should be able to constrain the proper motions fairly well there too. I actually think it probably makes even more sense to do this on differences between the coads rather than the coads themselves. That gets rid of a lot of blending from static sky objects. But it only enables you to do proper motion on those objects, not parallax. Now you still can get parallax for the other objects that you detected on single epoch images, but this lets you get proper motions at least on stars that are below the single visit detection limit or were too horribly blended to match ambiguously across different epochs. The other piece is much more theoretical, but I think it's at least a reasonable idea. So if you think about image subtraction, Eric will talk more about this later. It's reversible. You can reconstruct the original image from the difference and the template. And that means the template plus the differences, all the differences of all the epochs are together a sufficient statistic for the original images. You can just get them back again. And everything you could have learned from multi-epoch fitting should be doable on the combination of coads and difference images instead. And this is powerful because we do know how to handle blends on the coad. Well, okay, I don't know how to handle blends on the coad, neither does Fred, but we have ideas for how to handle blends on the coad, and we think they're pretty good ideas that may pan out. And on difference images, the blends will be much rarer because all the static sky objects, all the galaxies, all the stars that are barely variable, barely moving, will not cause nearly as much blending. So what do we do with those difference images? If we can predict the per epoch positions of all the objects well enough through the previous methods, the match source fitting and the yearly coads, then I think you can start measuring forced dipole moments with those positions on the difference images. And this is a lot like multi-epoch fitting, but instead of being sort of an iterative thing that you apply to a cube of images, you apply this, it's a linear operation to every image in the same way you do force photometry. So this means we don't have to write the code to essentially resort all of our images by position on the sky rather than per epoch. And it also means that we're not doing something iterative. And whether this works depends on whether you need something iterative. You can imagine if we're able to predict positions well enough that these forced dipole moments are on objects whose true positions are much less than a PSF width away, then those measurements are going to be very close to the match filter you would get by using their true positions with what we know about the PSF on the difference images. And I think that's going to be generally true for all but a tiny fraction of objects that probably move too fast and are too faint to be able to be detected on even our yearly coads. Once you've got all those forced dipole moments, you can do the final motion model in catalog space. And you can think of this as sort of a tweak up and a way to resolve and measure limits on motion for the faintest objects in the survey. So where does that leave us? Our current coordinate transformation fitting is behind the state of the art. I think what Gary described is pretty close to the state of the art for surveys like ours. But I think it's good enough not to be a limiting factor for many LSST science cases. And it's actually been good enough that it hasn't been a limiting factor for HSC. And that's because the HSC cadence is essentially take full depth in each band per night. And so we have been limited somewhat by not having a precursor data set that encourages us to explore trying to get that doesn't encourage us to get astrometry out of our data. it's definitely not good enough for some very important LSST science goals. And we have essentially nothing in terms of stellar motion fitting so far. I do think we have a credible scheme for getting the state-of-the-art match source motion fits. I think we could do that by exploring Gary's code. We could do that by extending our code in that direction as we originally planned to do. And I think we have a plausible scheme for pushing beyond that and measuring motions for all the objects, even the ones below the single detection limit. And I think it's a plausible scheme that doesn't require multi-epoch fitting. But most of this work on this last slide is not even started. And frankly, I'm worried about this. I think this is one of the risks for DM that remains, something that we have not gotten in shape at the level of many of our other algorithms. And I think you'd all be forgiven for being a bit worried about this too. And that's about it. Thanks.
Thank you, Jim. It was a very good talk. Do we have any questions? No questions. Sorry, I forgot to add a round of applause for Jim in our usual Slack channel. Okay, Gary, you have a question. I'll just unmute you.
Yeah, so do I understand what you would do is every unresolved source, capital S source, would also get a dipole estimate?
It would be, so every, I'm not sure if this terminology will help you, but the idea is that it's actually every force-host. For every object, everything we determine to be an object on the COAD, we go back and produce measurements on, traditional force photometry measurements on every single epoch image. And those are not necessarily matched in a clean way to the sources, which were detected on the single epoch images. And we would perform the dipole moments on those.
Well, do we have to worry that the flux of the stars is changing at the same time as their position?
Somewhat, but
extra degree of freedom.
I'd be surprised if that was enough to blow up the idea. I mean, for some stars, yes, but I think for the vast majority, that the level of variability is not enough to get in the way of this. I think at worst, actually having variability means you're going to be weighing the individual images incorrectly, not that you're, or weighing them non-optimally, not that you'll be making a systematic error.
All right, thanks.
All right, looks like I may have caught us up on time a little bit.
Yeah, you have. Well, I think we have no more questions for Jim. Thank Jim again for that talk.